Watch a wall of water crash against a riverbank, and the sheer force is obvious. Our everyday experience suggests that when something moves faster, whether it's a car, a baseball, or a rush of wind, it hits harder. It exerts more pressure on whatever gets in its way. But when we analyze the internal pressure of that flowing stream, this intuition fails. When a fluid speeds up, its internal pressure drops. It governs how airplanes fly, how a curveball breaks, and how nature balances its scales. To see this in action, aeronautical engineers use wind tunnels to measure exactly how air behaves as it rushes past an object. Let's look at a cross-section of a wing, an aerofoil. As it slices through the air, it forces the oncoming stream to split. Notice how the streamlines going over the top curve and crowd tightly together. That crowding tells us the air traveling over the curved top of the wing is accelerating, moving faster than the air passing underneath. Here is the paradox. The zone where the air moves the fastest is precisely where the outward pressure is the lowest. This creates high pressure pushing up from the bottom into the low pressure above. That differential is what we call dynamic lift. To understand the mechanics of that pressure drop, we need to strip away the complex shape of an airplane wing and look at a perfectly contained fluid. Consider a horizontal pipe with a narrow bottleneck. In a steady flow, water is incompressible. The exact volume entering the wide end has to squeeze through the narrow middle in the same amount of time. Physicists call this the equation of continuity. To move that much volume through a smaller space on schedule, the water has to accelerate. According to Newton's laws, mass only accelerates if there is a net force. For the water to speed up as it enters the narrow section, the fluid pressure behind it must be greater than the pressure inside the bottleneck. We can also look at this acceleration through the ultimate rule of physics, the conservation of energy. In 1738, the Swiss physicist Daniel Bernoulli decoded the math governing this exchange. As water hits the bottleneck, its speed increases, causing kinetic energy to spike. But total energy must remain constant. To pay for this new kinetic energy, the fluid's pressure drops. This is Bernoulli's equation, mapping the balance between pressure, kinetic energy, and elevation. In fluid dynamics, pressure acts like a battery of potential energy. When a fluid spends that energy to speed up, its internal pressure inherently drops. This invisible energy trade-off governs the bizarre bending trajectories we see on the cricket field or at a baseball stadium. When a ball spins, it drags a thin layer of air with its surface. This rotation fights the oncoming wind on one side, but adds to the airspeed on the other. That local speed increase creates a low-pressure pocket, resulting in a lateral push known as the Magnus effect. Bernoulli's exact mathematical balance assumes an idealized, perfectly frictionless fluid. Real fluids have internal friction, or viscosity. As layers of fluid rub against each other, they bleed off some of that kinetic energy as heat. While viscosity limits perfect efficiency, Bernoulli's core rule still dictates the system. Manipulating the speed of a fluid is the primary way to manipulate its pressure. From the lift keeping a 300,000 kilogram Boeing 747 in level flight, to the water in a narrowing pipe, the rule is universal. Fluid dynamics is a zero-sum game. Velocity and pressure are forever locked in an inverse relationship. Whether it's air over a wing or water in a bottleneck, the physical world strictly obeys the invisible scales of energy balance.